I don't know about that.
For yourself.
I'm pretty sure that everyone in this room is our friend. All right, well, welcome. If you don't know me, my name is Scott Fallstrom. I'm the faculty director of the Math Learning Center. And I was asked to give a talk after, I guess, somebody else bailed, so I'll start it off. Improbable probabilities. You don't understand what probability is, right? What's probability? Cricket. Chance, right? What is the chance that something will happen? So this talk is about things that you might be thinking initially one direction, but really it turns out being perhaps different. Let me give you an example. So mathematical dueling. You guys know what a duel is, right? The old style, you get a pistol, I get a pistol, we walk 20 paces, we turn around, we fire, and one of us is dead, and the other gets the girl, or something crazy like that. So I didn't want to have any violence in this talk. So what I did is instead of having a traditional, like we have pistols, I've brought in this version of a Nerf dart gun. It has a Mickey Mouse sticker on it, so no one could possibly imagine. This is not a weapon of mass destruction. It shoots small darts. These darts, I don't know if you can see them, they have red and there's a little bit of blue under, but you can't really read it until you put it in the magical decoder. And so this one, let's see here. First shot, if you could read that for me there.
Watch out.
Watch out. Yes. Again, without it, you can't read it theoretically. So this is what I've given to our daughters a while ago for Christmas. The problem is they don't like doing their chores. And actually there's one chore they hate most of all, and that's cleaning the bathroom. I don't know if you're in that boat too. If you're looking around, you're like, yeah, it's not that dirty. It'll probably last for a little while longer. So one thing that we've got is we have a way of determining that now. And it's with a Nerf dart gun. You see, basically, you set up a target across the room, and they go back and forth taking shots at it, and whoever hits it, the other person has to do the toilet. It seems kind of fun. So I thought, well, there's actually a little bit of math in there. Don't load the gun up, just put one dart at a time. If you've never seen these, this is just a quick load of dart. Okay, so it shoots a dart, and it actually shoots it pretty fast. But as you can see, it kind of started swerving off a little bit. So I thought of a game that would have a cylinder like this, and I'm going to put one dart in there, as you can see, one dart, and I will spin the cylinder. And to make it more fun, the idea is, yeah, that sounds pretty good. The idea is that you now don't know whether the gun will go off or not. And we'll make this deal, if the gun goes off at all, so no target shooting, because that would defeat the purpose. If the gun goes off, you have to clean the toilet. Okay? Is that a good thing or a bad thing? You have to clean my toilet. That's a bad thing. Okay, so some of you are like, I do not want that to happen. I do not want the gun to go off if I'm here. Okay, so you load the gun, right? I have spun the cylinder repeatedly. I will now... It did not fly out. If I was to now ask you, now I give the Nerf gun to the next child or to the next person in the room, and they have two choices. One is they spin the cylinder again, and the second is they just pull the trigger. Which one would you rather do?
Pull the trigger.
Would you rather just pull the trigger, or would you rather spin the cylinder again so you got kind of a fair chance? What do you think? How many of you would rather just pull the trigger? And it's okay. It's okay if you're wrong or not wrong. It's not really. Some of you are, I just pull the trigger, man. That's it. How many of you are like, no. Spin it again. I do not want that toilet. Oh, we are split. Wow, it's like half and half. Okay, well, let's see how this looks. Anytime there's a question like this, we should check out the mathematics. So here's kind of what it looks like, right? I've got one dart in here. Okay? And we spin it around. What's the probability the dart will fire for the first child? Well, the first child who pulled the trigger after spinning had a 1 in 6 chance that it would fire. Okay, 1 out of 6. Okay, if the dart fires, remember you got to clean my bathroom. So 1 out of 6. So let's write that down. 1 out of 6. Okay. Now if it didn't fire, and you guys who said I would just pull the trigger again, what are your chances? 1 out of 5, right? Because there's only 5, right? You know you weren't here because it would have gone off. You had to be somewhere else. So when the next one goes, you've got a 1 in 5 shot. What if you spun the cylinder again randomly and then pulled the trigger?
1 in 6.
You're back at 1 in 6. So the question really is, which one of these is better?
1 in 6.
1 in 6 is about 16.6%, and this is about 20% chance that the gun goes off. Which one of those would you rather do? Remember, toilet is on the line. Cleaning a toilet. You would probably be saying, I want the least chance possible of cleaning the toilet, right? Smallest chance. I want that thing to go, okay, I'm up here. Which would mean you would spin. You'd spin it again. All right, fair enough. This gives you kind of the idea, okay? And since I haven't moved at all, didn't go off. All right, I'm good. Now again, we could keep talking, right? What would it be for the next person? 1 in 4, which 1 in 4 is 25% of the time. That person's like, yeah, spin it. No, spin it. Don't just give me the, no, because eventually what's going to happen? It's going to go off. Eventually, at some point in time, I mean, it just has to. Oh, there it is. And it did. So, all right, now you got the thought process. I'm going to set this down before I hurt myself. I know it's only a Nerf gun, but things happen. Okay, here's the idea now. Picture this. Pretend I have the Nerf gun because, okay, I've now put in 2 darts. Okay? I spin the trigger, or spin the cylinder. What is my chance now if I just spin it and pull? 2 out of 6 now, right? Because there's 2 darts in there. I got 2 chances out of 6. So that brings us up to, what, 33%? 33 1/3, but 33%, okay? So now I'm going to ask again. If it was up to you, and you were handed the gun, would you just pull again, or would you spin and then pull? So how many spinners? Remember the first time, spinning would have been better. Okay, spinners now. How many would just pull? Some of you are just pulling. Okay, here we go. So remember, if it did not go off, you must have been in one of these 4 empty spaces, right?
Right.
So if you were here, and the cylinder rotates, the next one would fire there. How many of these 4 are going to cause the dart to fly out on the next shot? 2 of them. See, if I'm here or here, the first shot didn't go off, but the next one is going to. So what is that? 2 out of 4? Toilet's on the line. What would you rather do? Spin or pull? Spin. Look at that. 33%. Still not great. 1 in 3 goes off, but it's better than 1 in 2. Okay. So first one was better to spin. Second one, better to spin. Right? Does it kind of feel like there's a theme here? Maybe like we need to get to a spin class or something like that. Okay, hold on. This time I'm going to put a couple darts in there. Don't mind that, just a couple darts. And I'll just put them right next to each other because just 2 darts doesn't really matter. What are my chances if I pull on the first one this time?
2 out of 6.
Didn't change. That didn't change. Okay, same question to you. I'll stop asking eventually. How many of you, if you were handed this gun, would spin it and then pull again? How many of you would just pull the trigger? Oh, see now, some of you are like, oh, I've got to be doing something. The title of the talk was Improbable Probabilities. It was spin for the first one, spin for the second one, so I'm just gambling here. I think it's going to go the other direction. Now, let's see what happens. How many non-firing ones would there have been?
4.
4? So if I ended up pulling the trigger and nothing came out of the gun, I had to be in one of these 4. out of those 4, how many of those spots, if I just pull the trigger again, is it going to go off?
One.
Only one of them. Only being here because it'll move me to the next spot. Oh, so my chance is actually 1 in 4, which is 25%. Oh, yeah. Now that violates what we did the first 2, right? See, the first 2, it would be better to spin it again. But now that I put 2 darts in right next to each other, it's actually better to just pull the trigger. It's like toilet roulette, right? Similar to the other types, but not exactly the same.
Do you put 2 bullets with your darts?
Oh, I don't tell them how many I put in. They started getting a little too good with it. Did the location matter?
Yes.
As it turns out, the location, I just said, oh, I'm going to put 2 darts in there. It actually mattered where I put them. Did I put them right next to each other? Because then it was better to actually just pull the trigger again. Or is it better apart? It's better not to. What do you think would happen if I put in 3 darts? 4 darts? 5 darts? Does your decision change then based on how many I put in?
Yeah.
Right? I decided not to put down 6 darts because all right. Now we get into the fun part. A Nerf Duel. Now it would have been a normal duel, but again, we're trying to stay with anti-violence today. So, Nerf Duel. Each person gets a Nerf gun. I've put a small picture here to demonstrate how they would start. They would pace away from each other as faceless creatures and turn around and pull the trigger. Okay, now here's the problem. I'm giving them some pretty nasty looking Nerf guns. They're actually not very accurate. And we're going to have these people each take 20 steps, then turn around and shoot. I mean, your chances are not great. So I'm going to say that person A has a 30% chance of hitting person B. Is that a good chance or not really? I fire 10 times on average, I'm going to hit about 3. Okay. If I can do that in the game of baseball, I'm in the Hall of Fame. But in the Nerf gun, that's not so great. How about person B? Person B has a 10% chance. And you met these people. You know who they are. They're horrible at most, right? You're like, okay, all you got to do is pull the trigger and shoot. Huh? You know, it's flying all over the place. So here's what we're going to look at. In this type of a game, instead of having everybody walk, we're just going to stand and face each other. And basically, I'm going to pick somebody to go first. And then they shoot, then the other person shoots. Then they go back and forth until somebody hits. Because can you imagine what could happen? Could this go on for a while? Oh, you missed. Okay, your turn. Oh, you missed. Okay, hold on. Oh, you missed. All right. So what we're going to do is we're going to look at, if person A goes first, what is the chances that they're going to win? And if person B goes first, what's the chance they're going to win? With A, person A has 3 times the chance, a 30% instead of a 10. 3 times the chance. Will A have 3 times the probability of winning? One person hits 30%, one person hits 10%. Will they have 3 times the probability of winning?
No.
Like way off?
I don't know. Just what we have.
You're just like, no. Okay,
All right.
well at least we have an idea. So here's the solution. Now for those of you who are in pre-calc or calculus, you get to see these. Now if you happen to take Math 52 or 95, you also got to see these. Because what happens is we end up with a sequence of numbers that goes on forever. And we're trying to add them all up. So take person A, for example. Remember how often did they hit? 30%. So that as a decimal would be 0.3. So this would be the ways that person A could win. Now go with me. If they fire first, they have a 30% chance of hitting, which means right off the bat the game's over. Okay? But what happens if they don't hit?
They miss.
There's a 70% chance they miss. And in order for them to be able to fire again, the other person also has to miss. So that's a 70% on A, a 90% for B, and then person A hits. Okay. Now remember, this game could go on for a while. So the next one over is I miss, they miss, I miss, they miss, and then I hit. So see all these little exponents there? It's just summarizing what's happening. Miss, 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 hit. And this gets even worse, right? Now you're like, this is where a parent is starting to say, okay, we're going to find something else to do today. Miss, 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 hit. And notice the dots. What does that mean? There's more. I didn't stop. It could keep going, right? Can you imagine how horrible these shooters are? Now let's go with person B. So remember, I'm person A. I got a 30% chance of hitting. Person B over here, what's their chance? 10%. But in order for person B to even shoot, person A has to miss. And that happens 70% of the time. So for me to win as person B, that person has to miss and I have to hit. Or miss, 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 hit. Or miss, 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 hit. And it goes on forever. Now I'm going to leave this, again the slides are out there for you to try this at home if you'd like. But one thing you could do is realize this is what's known as a geometric sequence. From one term to the next, I keep multiplying by the same thing over and over again. So I could add those up very quickly, and again, pre-calc or calc, you might have seen this formula. So you could use that here. Go right ahead. But what I wanted to do is for people who are maybe in lower classes, like I don't know what that formula even means. What is A? What is R? Perfect. For now, I'm going to show you a different way to do it. And it goes like this. Looking between A and B, they actually look very similar at times. Do you notice strings of 0.7s and 0.9s in each one of them? This one has 0.7, 0.9, 0.7, 0.9, 0.7, 0.7. Looks very similar. If we can find a way to put them together, we might be able to find this sum without doing pre-calculus or calculus. Just with basic algebra. And that's what I said the level of the talk would be, so that's what I'm going to do here. Take a look at B. You see B right here? And what I want to do is take a look here. See this 0.7 and 0.1? And I want you to tie it into the one right above it. Notice the 0.7 matches, doesn't it? There's a 0.3 instead of a 0.1, and there's also supposed to be a 0.9 up there. So what I'm going to do is I'm going to take the probability of B, and I'm going to multiply it by a 0.9, 0.9. That'll put one of those up there. And I also need the 0.1 to be a 0.3, which means I'm going to also multiply by the number 3. And if I do that, every one of these terms down here on the bottom will become one of the terms on top. Except for one piece, and that's the little 0.3 at the beginning. It kind of screwed everything up. So I'll just add it on at the end. So what I've done is I've seen a connection, and I use that to create this new piece. For those of you in Math 30 or Math 64, all we do now is substitute. I have the probability of A, which is this chunk, plug it in, plus the probability of B, and it's supposed to equal 1. Combine my like terms, divide, and I end up with the probability that person B wins is about 19%. Now remember, where did B go? Did they go first or second?
Second.
They went second. So over here, person A has a much greater chance of winning. And since only one of those people can win, if person B wins 19% of the time, person A must win 81% of the time. So that's what we have here. Now notice, did it matter who went first?
Yes.
Right? If person A goes first, I got a 30% chance of hitting right off the bat. And in order for B to even go, I have to miss. If we reverse that and say person B goes first, that might change things. But remember what we said, 3 times the chance. I got 30% to 10%. Does that mean 3 times the probability? 19% to 81%. Let's round those. 19% is pretty close to 20, and 80, about 80. So 20 to 80, that's not 3 times, that's 4 times. Much better chance for A, as it turns out. So I went through and I redid it. This time I let B go first, so they have a 10% chance of winning right off the bat. And then miss, miss, hit, miss, 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 hit, and so forth. This time when I got done, the probability that A wins went down. The reason it went down, of course, is because there's a 10% chance right off the bat that the other person wins. So it came down to 73% and 27%. It's actually pretty darn close to 3 to 1. Well, I needed this piece. Now, as you can see, person A has a much better chance no matter when they start, right? Almost a 75 to 80% chance of winning no matter what. And that makes me very sad. So we want to try to do something to cheer up person B, who really doesn't have a good aim in this game. So I call this next section Ménage à neuf. Now, that's French, in case you do not know. So now this is 3 people in a duel. And if you've ever watched some of those old westerns, sometimes, right, there's the good, the bad, and the ugly, and they're all walking up and they're looking, you know, and they're, who's gonna? So this is now 3 people. And I want to go over the rules of what we will now call a truel. A truel is just a duel with 3 people, so that's the idea. So here's the way it works. I got all 3 people, and in order to keep the numbers okay, I'm going to keep person B as still being the same as they were before. What was person B? They were 10%. Person B was 10%. Person A is 30%. Okay, I'm going to bring a new person in, and person C is amazing. They don't miss. No, they don't miss. And you've seen those people on TV, maybe they're like, oh yeah, he got you. Okay? So here's the idea. Whoever goes first, and I'll randomly pick who goes first, they pick the direction. So they could choose, if person A is the one I choose, they could choose to go in this direction, and then it keeps going in that direction until it's over. Does that make sense?
Mhm.
Or they could choose to go in the other direction. Remember, I'll put it up here. A was 30%, B was 10%, and C was, oh, they're awesome. Yeah, they're awesome. If you were person C, and you got to go first, who are you going to shoot at?
A.
A? Guaranteed? Is that your best chance? Because if you shoot at A, how often do you hit? 100%, so they're out. Okay, so A just lost. That would really suck, by the way. If you're in a truel and you get up against this guy and he just decides to aim at you, thank you, go home. So now it's up to B and C, right? C just shot, the order stays the same, so B gets 1 shot at C, which has 10% chance. And if they miss, C shoots and it's over. So that was fun. It's over very quickly in this case. So that means that C, if they shoot this direction, has a 90% chance of winning, wouldn't you say? Remember, the only time they lose is if this guy hits, which is pretty small. If they decide to go the other direction, they're going to knock B out, and A has a chance to shoot, which means you're really comparing, do I want 90 or 70, and most of you, you actually were right on. You said, no, shoot at the guy who's got the best aim. Good choice. All right. Person A is pretty similar. Think about what happens. If you are person A, who do you want to shoot at?
C.
C? Okay, so you want to shoot in this direction here, and why is that?
Because B has a 10%.
B only has a 10% chance, and pretty much if you miss B, C's gonna be around, man, right? I'm sorry, your game's pretty much over. But what's worse? if you aim at B and you hit. Picture that. Do you see it?
Yeah.
I got a 30% chance. I'm doing it, man. I'm going for it. Haha, I took out B.
And then C should.
Pew! You're out. Okay?
That's cute.
So down. Okay, so you guys are kind of thinking, okay, go towards C. So that means we're going this direction. That means if A hits, which is 30% of the time, aren't we, because C is now out, aren't we right back into the A and B that we just did a moment ago, where A just A and B, boo, 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 could go on for a very long time. These are horrible shooters. But look who actually goes first in that case. B goes first. And we already said that when that happens, B has a 27% chance and A has about a 73% chance. Okay, still pretty good. Of course, we already said if A goes to B, it's pretty bad. I put a picture up there, you remember B with the teardrop rolling down his face. So sad. Now I want you to think, who would you aim at if you were B? You are the
C.
worst shot in the, you are the worst shot in the game.
So I would try C.
He said, try C?
Yeah.
Okay, that's, it's a great question. Okay, remember C is gonna hit no matter what, so, yeah? Do I have consensus? Should we shoot at C?
Yes.
Shoot at C, okay. That means if I shoot at C, how often do I hit?
10%.
10% of the time, but 10% of the time now I'm locked in a duel with A, and A gets to go first from that point, right? Pew, 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 okay? Did anybody at least think this way? And I'm gonna tell you why it might be okay to think this way. Hold for a second. I suck at this game. I suck so bad, I'm pretty much gonna miss this guy. A has a much better chance of taking C out than I do. Why, I bet I'm going to miss him. Pew, I missed.
Wow. Yeah.
What's the chance of A taking C out?
30%.
30%. What was my chance?
10%.
10%. Now that I've planted that seed, I'd like you to think. This is now you, and if you need to picture it like, how could this happen in real life? Picture Survivor, the TV show. That's real life, man. That's real life. Or Big Brother, with those competitions. You know those stupid competitions they have? Yeah. Again, real life. So I will now ask you as a group, which way would you shoot? You are now person B.
Yeah.
A.
Shooting at A
Yeah.
or shooting at C?
A.
A? Okay, all in favor. I'm shooting at A. Who's shooting at A? No peer pressure here. If you don't believe this, don't raise your hand. 2, 4, 6. Wow. That's like 90%. Okay, who's shooting at C? No one.
I guess. Yeah.
No one is shooting at C because you realize person A is a better shot. You kind of want to get them the chance, right? Let's check this out. Should we use a little math then?
Yes.
I think we probably should. That's a good thing that we're here. You hit 10% of the B. What do you want to do? So here's person B grabbing the help button. Quick, help me out. All right. Well, let's see. Let's do the math. Person B shoots at A first. Shoots at A. And let's see here. Then C shoots at B. It's all over. That only happens 10% of the time. If B misses, then A shoots at C. So we need to calculate that. Remember, how often does A miss? I'm sorry, how much does B miss?
90%.
90%. It's pretty much guaranteed they're going to miss. Okay. So then I figure out what is 90% of the chance that I lose. That's 63%. But if A does hit, which I hope happens, right? I just missed. I hope A hits so that I have a chance. Okay? Then I get to shoot first in a duel, and I already know that chance. So I have about an 8% chance of winning. 8% if I shoot at A. All right. Shoot at C. Here we go. B shoots at C. How often do I hit? 10%. Now that's not great, but if that does happen, I win 19% of the time. That's not good. Okay, well, what if I miss? If I miss, which is 90% of the time, what are my chances? Remember, if I miss, right, and shoot at C, what's going to happen? C is going to, A is gone. I now have one shot coming back, but the only way I get that shot is if I had missed. And I missed 90% of the time and I hit 10% of the time. My overall chance is now 9%. What was it in the other one? 8%. The best chance is actually not what you all thought it was. The best chance is if you shoot at C. Because my chances are 9% compared with 8.1%. Now, would you like to increase your chances?
Sure.
You're B, you're the worst shot in the game. You need to do everything you can to increase your chances. Sneaky ninja. Person B is sneaky and really does not want to do the toilet. Remember, whoever loses does the toilet. Okay. Best chance to win is when B shoots at C and misses. We saw that was a 9% chance. That rate could go up if person B intentionally misses. So here's the thought. At that point, if I say, oh, I'm shooting at C and I intentionally miss, C kills A, and I have a 10% chance to win coming back. You see, the reason it wasn't higher earlier is there's actually that very small 1 in 10 chance that I actually hit C accidentally. So this is the strangest duel ever. I am the worst shot with this thing ever. And my best chance to win is to take and say, okay, that guy hits all the time. I'm going to aim at him. Oh, I missed. Me shooting my gun into the ground has increased my chances of winning. And you don't get to say that very often in a shooting game. First time I saw this, I was like, yeah, right. And then I ran back here and I'm like, oh, crud. This changes everything. Again, a little bit improbable. Based on the time, I'm going to have to go up a little bit here. So I have to adjust a little bit, that's all right. All right, so this time we've done some Nerf dart guns, and some of the things are probably different than what you thought, because you thought initially, oh, I need to do this. No, I actually don't. I need to go the other direction. So to do a little prime time, I want to get into some numbers here. What are prime numbers? You guys have seen them, right? Prime numbers? Only divisible by 1 in itself. Okay. Could they be negative or? No, so we're talking about non-negative numbers, so positive numbers. Okay. So what are the first few primes? Do we know them?
2, 3, 5.
2, 3, 5. Okay. Is 1 prime?
No.
Why not? I bring this up because I watch television. What is the second prime number?
3.
Okay. It's good that you think that. I'm going to click on this, and if everything has worked well, we'll get to see it here. I haven't done a PowerPoint with embedded links before, so it's kind of, oh yay! Oh, Microsoft Explorer. Oh well. That'll have to work. I don't have to adjust the volume here, so I don't want to be too loud. Let's see here. There we go. It's loading.
$2.99 burger and shake. Classic combination.
Oh, you know what had a classic combination? My high school locker. 16, 35, 2. 16 is the square of 4. 35, that's the age where you can be a congressman. 2 is the second prime.
That is so complicated.
It's clap.
You see, the second prime is 2 according to Sonic. And since this was on television, I know it must be accurate. All right, so we kind of know those guys are a little cracked up. 1 is not prime. How come? That's cruel. For most of you, it's probably because my teacher told me it's not prime, and I answered it one time, I got it marked wrong, so I know it's not because I got marked wrong.
Is there a fundamental law in multiplication or whatever, counting, where 1 is like the equivalent of like 0 or something like that? You know what I'm?
Somewhat. The idea is the fundamental theorem of arithmetic that says if you factor numbers
Yeah.
into primes, that you and I will end up at the same place. That means if you factor 60 and you start with 2 times 30 and I start with 3 times 20, we're going to end at the same place eventually. But that also means that the factorization has to be unique. And if you had a bunch of 1s in yours, maybe you had 1 times 60, and I didn't have any 1s in mine, and 1 was a prime number, that you and I would have a different prime factorization. So therefore, 1 cannot be prime. It would violate the fundamental theorem of arithmetic, which is kind of cool. Also, 2 numbers that are relatively prime if their only common factor is 1. So can you think of 2 numbers that are actually relatively prime? Give me
8
2.
and 9.
19,
19 and
11.
5. 19 and 5 would be relatively prime. By the way, if you pick 2 prime numbers, they're guaranteed to be relatively prime.
10 and 3.
10 and 3. There's a number that's not prime, 10, and a number that is prime, 3. Could you think of 2 numbers that are relatively prime, but both of them are not prime?
8 and 9.
Let's see here. 8 and 9. Well, let's see here. 8 is 2 cubed. That's a bunch of 2s. This one's a bunch of 3s. So these are actually relatively prime. Mathematically, we write that the greatest common divisor is 1. So that means the only factor they have in common. Did you guys learn greatest common divisor or greatest common factor? Factor? They're synonyms, so it's not like I violated anything there. All right. All right, let's take a look then. Here we go. Yeah, so I'm not going to get to this, but here's the idea. Take a hat, and I'm going to put numbers into the hat. Okay? And into the hat, we're going to draw and see if we have numbers that we can find that are relatively prime. You're going to draw 2 numbers out. So you can kind of picture this, and again, for time's sake, I'm not going to get into this. Key points, how many prime numbers are there?
Infinite. A lot.
Infinitely many. It's more than a lot, but yes, I like that. There are a lot. There's also infinitely many composite numbers. And if they're relatively prime, again, they only have 1 in common. So if you want to find if 2 numbers are relatively prime, since we don't have a hat, I'm going to select the numbers 1, 2, 3, 4, and 5. And if you picture me putting them into a hat, and you draw 1 and I draw 1, there's 10 different ways that we could choose those 2 numbers. I could choose a 1 and you choose a 2, 1 and 3, and so forth. These are all the different ways we could do it. I put a little note there because if you're thinking there's actually 20 different ways, just remember at the end, you end with a 2 and I end with a 1, it's the same, or I end with a 2 and you end with a 1. So we don't need to think about that. How many of these pairs are actually relatively prime? Let's see here. The number 1 and 2, relatively prime?
Yeah.
1 and 3?
Yeah.
Mhm.
Sure.
Are there any that are not relatively prime?
Well, 142.
2, 4.
20, it looks like 24, but it's really a 2 and a 4.
Oh,
The 2 and the 4 together are not relatively prime. They share a common factor of 2. But a 2 and a 5, they don't share anything. A 3 and a 4 don't share anything. That's it. 1. So if I had the numbers from 1 through 5, your probability of drawing relatively prime is 1 in 10. It's not great chances. Let me put some more numbers in there. That'll probably help. Okay, so if I put in the number 6, just one more number, I put a 6 in the hat. Well, now there's 15 ways to select them, but the beautiful thing about the number 6 is it has a factor of 2 and 3, which means relatively prime, now more of them fail. Like if you drew a 2 and I drew a 6, sorry, we've got something in common. If you drew a 3 and I drew a 6, we have something in common. All right, so let's see here. What I'd like you to do is, you guys have something to write with? Or at least something that will keep it secret here. I'm going to call on a couple of you, and I'm going to say, we're going to do the numbers from 1 to 100. Okay, so I'm going to pick on two of you, and you're going to pick a number from 1 to 100, and I want you to write that number down. Okay, it's going to be kind of random in that sense. So I'd like you to pick a number between 1 and 100 and write it down, or at least have it in your mind if you don't have something to write. Okay? And what I'm going to do is I'm going to check and see if they are relatively prime, and the way I'm going to do it is with this website, which will allow me to calculate the GCD very quickly, because otherwise sometimes the numbers get big and it's a little harder to find their greatest common divisor. All right, so I need 2 people. Here we go. Do this a couple times. Okay, so again, I need some people here. So raise your hand if you've got a number in mind. Okay, 1,
31.
31, and 2.
52.
52. 31 and 52? Relatively prime. Okay, so I'm not going to pick the 2 of you again. I need 2 other people. Let's try it again. Fallstrom?
66.
66. Oh, this has 2s, 3s, 11s.
85.
85. 85. It's got a 17, 5. If you want to check, we'll come over here and we'll check really quickly. Let's see here. I need 85. And what do we say, 66?
Any number.
And the GCD is 1. Got lucky there. Do you notice that when I picked these people at random, the person who picked 52, I could have put with the 66. Actually, I didn't know that. But if the 52 went with the 66, they have a 2 in common. So that would have failed. So right now we're good. We're 2 for 2 so far. But again, it could have not gone that way. Let's get just 2 more people maybe, and let's have one more chance here. One more chance. What do you think?
97.
97. Going for the high prime.
4.
4. So pretty much, if you would have picked any even number at all, we would have been good, but 3 for 3. Right. Now, if I included the numbers from 101 to 200, now you're picking a number from 1 to 200. Again, what I notice is some of you may know some of the primes, maybe. So some of you picked primes, which makes it very hard to find something that doesn't. But again, if I go bigger, right, now you're like, oh, it's harder for you to factor and find those primes. What if I went beyond 200? Maybe I'll go up to 500. A number from 1 to 500. Do you think that your chances are going up or going down?
Great chances.
What I'm saying is, what are your chances of finding 2 numbers that are relatively prime? We were 100% here. All of our chances were 100%. We nailed it. So I'm wondering, do you think we're going to be able to go more? Is it going to be a pretty strong likelihood when I add more numbers? It's going to go down? Okay, so if I go from 1 to 1,000, we're thinking it's going to drop.
Yeah.
And if I go from 1 to 1,000,000,
Worse.
and from 1 to, I don't know, here, I'll give you a number. That's right. I want you to picture this. I'm not going to put every positive integer in a hat. All of them. Can you think of all of them? Okay, that's what we're talking about right there. Think of all of them as you go. And, okay, see, we already did that one. Check. We put all of them from 1 to infinity. So now what I want you to do is, here's your options. Less than 40, between 40 and 60, between 60 and 70, 70 and 80, or over 80. Remember, we hit 100% with our small sample. And F is, I'm not sure, but maybe it will involve picture pi.
Yeah.
Okay, so I'm going to let you choose A, B, C, D, E, or F. Mark it down on paper. Not that I think you're going to cheat, change your mind, or anything like that. It's what you think is it going to be. I went from 1 to infinity. You guys said it keeps going down, so maybe you're going to mark A because you're like, it keeps going down. Maybe you were like, we were at 100%. If I put in infinitely many numbers, I'll be at about 50%. Okay, but you have to have some kind of feeling for this at this stage. And some of you might just be hungry.
Yeah.
Maybe I should have put a picture of a pizza pie. And you'd be like, oh, I already had some of that. I'm not as hungry. I'll concentrate on math. Let's see. Let's see here. Well, for those of you who are in algebra, here's a little toss your way. How does algebra come in? So from math 30, you might remember 1 minus x times 1 plus x. Difference of squares, as they call it. Sometimes you might be going the other direction, so some of you might think of it as factoring, okay, as I go that way. All right, well, it turns out there's a beautiful pattern there. 1 minus x times 1 plus x squared, all the middle terms kind of cancel out just the way they did, and I end up here. And then I do it with an x cubed, I get to x to the 4th. I do it with x to the 4th, I get to x to the 5th. It's beautiful. It's really beautiful. Because notice I multiply everything by 1, and I just write this down. And I multiply by negative x, and each one just goes up 1. Almost all the x's cancel out, and I'm to the end. So this last one, I could write it as, see this how it equals 1. And that's because, do you notice what I changed? I said I'd go out to infinity now. Just go all the way. Tell me when you get there. Okay? And notice here, I did say the absolute value of x has to be less than 1. And those of you in calculus understand that what we're talking about is the numbers, as you square them, if they're bigger than 1, they keep getting bigger and bigger. But if they're smaller than 1, they get smaller and smaller. And you can kind of do that. So here's the beautiful piece. I can rewrite it with a fraction. And I could have the 1 minus x on the bottom, or I could have the other piece on the bottom. It's very similar to a geometric sequence. Well, you might even notice this. You're like, oh, my teacher used that when we did geometric sequences. Right there. Nothing against geometric sequences. I think they're kind of cool. All right? So what are the chances? Now we have to do a little math. We had a rough calculation. First ones were 10% and 70%. We hit 100. So here's the idea with probability. Here's where probability comes in. What are my chances that a factor, that the one that you grab and the one somebody else grabs, that they share a factor of 2? That's the first prime we said. Well, what are your chances of getting an even number?
25%. Oh, is that 50?
Even number, 50% of the time, so 1/2 for your number. And because there's infinitely many, 1/2 for the other number. So that means really the chance of you both getting an even number is 1 in 4. The chance it will not happen is 1 minus that. So what's the probability they do not share a factor of 3? Well, your chance of getting a 3 is 1 in 3. Mine is 1 in 3. So the chance it does not is 1 minus 3, 1 over 3 squared. And the same, it goes up for all the primes. I do this for each prime number. How many primes are there? A lot.
More than
Exactly. So I actually have this really long piece. And I have to multiply all of those because I do not want factors of 2, and I do not want factors of 3, and I do not want factors of 5, and I do not want factors of 7. And each one of those looks like the 1 minus x from the previous page. That means each one of them I could rewrite with that beautiful fraction. A small little fraction, right? It only goes on forever. Let's see what that looks like. Yeah, so I put a little picture up there of what some of you, your faces actually look like right now. It's good. You're like, wait, what? I thought you were trying to make this easier, simplify it. Well, sometimes you have to make things more complicated in order to simplify them. So what I had originally is here. And I'm just going to multiply those infinite series out. There's only infinitely many of them, so it'll be pretty quick. Right? Now you may not see it. You may not see it, but take a look. As I begin to do the distributive property, I would have 1 times the 1 times the 1 times the 1, and I do that infinitely many, I get 1. The next one I'd have a 1/2 squared times 1 times 1 times 1. Then from here I could have the 1/3 times the 1 times the 1. I'm going to end up with 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared, plus 1 over 6 squared. 6 comes from the 2 and the 3. Plus 1 over 7 squared, plus 1 over 8 squared. It's a really nice pattern. And it's not actually that bad. We'll just distribute it all out. Yeah, that's the face you made. Let's see here. You multiply it all out, this is what we end up with. This was infinitely many infinite multiplications, and I end up just here. That's kind of nice. All I have to do is add this up. And those of you who have calculators, you could try this. 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared. And you just go out for a while, and you'll find the answer. Yeah. So all we have to do is find this infinite sum of the reciprocals and then squaring them. Some of you are grabbing calculators, like, yeah, I'm trying that. Go right ahead. So here's a little history, because every time I give a talk, I try to give a little history as well. We're not the first to ask that question. What is the sum of the reciprocals of the squares? First came out in 1644, Pietro Mengoli, and it was solved in 1735. This problem lasted 100 years. Some of you do math homework and you're like, this problem took me like 10 minutes. I can't believe how long it is. This was a 100-year problem. It went to a group of specialists in what's known as Basel, Switzerland. They were known as the Bernoullis. If you've never heard of them, they've done a whole lot, not just in math, but in science. There's a Bernoulli effect of weather. The older one, Jacob, came up with the Bernoulli numbers, wrote a book on probability. He's the first one to write about this problem that was ever published. It was like, oh yeah, 1689. His brother Johann worked on infinitesimal calculus. Pretty much he devoted his life to it, to finding the sums of sequences and series. What some of you, if you're in Calc 2, you're like, I can't believe we have to spend an entire chapter on it. This guy spent his entire life on it. Okay? So Johann had a couple sons. Almost all of the kids in this family were mathematicians or physicists, astronomers. They all went into the sciences. There was one who was an artist, but that's all you can find about him. He was an artist. Done. That was it. So cool. But this guy, Johann's son Daniel, created principles in physics. One of them was used to create what is called a Bernoulli box. Does anyone remember these old devices for computers? You used to put them in and they would store your data. Now, can you imagine back then telling someone, no, just put it in the cloud? Yeah, right, put it in the cloud. The Bernoulli box had a disk that was this big. It's bigger than the size of a sheet of paper, and it held 20 megabytes. It may not seem like a lot, but these other ones over here held 500 kilobytes. So you would need a stack of hundreds to get up to this piece. It was a beautiful thing. It also defeated the purpose. If you ever used these old ones, you might remember where it made that horrible noise. That was where the head of the disk hit the diskette and ruined all of your everything. Because of this principle in physics and fluid dynamics, he created a system that would never have that problem. Unfortunately, he did not market it very well. It was made by a company called iOmega. And those of you who were around in the 90s remember iOmega zip drives, which were small, blue, beautiful disks that held 120 megs. They were awesome. Anyway, that's history. And we invited the computer science folks, so I thought I'd throw a little computer science in there.
Is that a floppy disk?
That is not floppy. That was a hard disk. This you could not put in your pocket. This thing was cute. It was beautiful. I owned one. Unfortunately, it was way long afterwards. I found it at like a yard sale. I was like, Bernoulli? I've got to have this. So it led to this problem. Remember I said it was a 100-year problem? When a problem lasts for a while, when it has teeth, they name it. This one got a name. It was named after the location. It was called the Basal Problem. Now the Basal Problem had a whole bunch of really famous people try to solve it. Yeah, the Bernoullis, but you might have heard of Leibniz. Anybody heard of Leibniz? He invented calculus along with Newton. So yeah, he tried it. Did he do it? No, he failed. How about James Stirling? Yeah, Stirling was very famous at the time. Did a whole bunch with confirming the math of calculus and why it works. He failed. De Moivre. If you guys were at my last talk, I talked about De Moivre's theorem for finding roots and powers of trigonometric numbers. He worked on it, he failed. It was pretty much a collection of the top minds at the time, and nobody could solve it. What happens if you're a teacher and you can't solve a problem?
Give it to your students.
Thank you. You give it to your students and you say, here's your homework. Right? So some of you, if you go home and you're like, this is so hard. Yeah, I know. I couldn't solve it. That's why I gave it to you guys. Maybe you'll think of something I didn't. So that's what one of the brothers did. Johann gave it to his student. His student's name was Euler. Leonhard Euler. Bond, James Bond. Yeah. Anyway, this is a picture of him. He's kind of he's a different looking character. But due to their location, it was called this. Euler solved a problem when he was 28. 28 is a perfect number. And his techniques weren't shown to be valid for another 6 years. 6 is also a perfect number. You could not have a more perfect problem than this. By the way, the next, Euler had a lot of things around perfect numbers. The next perfect number is in the 400s. So he didn't live long enough to see that one. So here's the way the Basal problem went. Bernoulli brothers are fighting with it. He turned it into trigonometry. That's what Euler did. Do you remember the problem? 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. And Euler looked at it, and what did he say? Trigonometry, that's where the solution is. Yeah, I don't know if I would have seen that. For those of you in Calc 2, some of you know right now, you're like, oh, I could rewrite sine as a polynomial. I remember sine is a curve that kind of goes up and down like this. It is not a polynomial, but I can approximate it with polynomials so that I might get a curve that's close to it and does something like this. But if I go out to infinity, it matches perfectly. It's a beautiful expansion. I didn't see the trigonometry in this one. So I wanted to give you guys a little test and see if you saw what Euler saw. This was before calculators. So no calculators. I need you to look at these numbers and tell me what they are.
I have just
Pi in the first one, do you see the pi? 3.14, okay. If you're in trig class, you might have seen this many times. This is pi over 2. Pi over 4. Somebody be like, how are you knowing that? Just because you come familiar with it. If you do trig inverse functions, you will come up with this number on your calculator, and it's helpful to see the connection. Okay. 0.318309.
I see.
Yeah. It's really close to what fraction? Really close to 1/3? Yeah. Pi is really close to 3. This is actually 1 over pi. Yeah. I was like, what? I didn't see that. 6.28, anybody got that one?
2 pi.
2 pi, okay. 0.866, trig people.
Root 3 over 2.
Root 3. See that going through? 1414, 2121.
Root 2.
This is square root of 2. And the most famous one right underneath, some of you might remember this, this is root 2 over 2. So on the unit circle, this one comes up a lot in trigonometry. I threw a few others in there for you, a little square root of 3 action. You know, this, anybody catch this? This is E, right? Part of the E club. 0.7692307692307692332. Notice it repeats though. Do you see that? Do you see that part? 0.769. It repeats in 1, 2, 3, 4, 5, 6 digits. Things that repeat in 6 digits happen with recurring regularity. So we can turn that into a fraction. This one happens to be 13ths. It has to be a multiple of 6 add 1. So it's either 7, 13, 19. 0.29411767057. Yeah, I know. That one, I believe, is 16 digits, and then it repeats. You see the 29411? 29411? I didn't spot it at first either, but I did see it afterwards. How about this one? 232323232323. Definitely repeating. The idea is this. Back in the day, you didn't have a calculator. You couldn't check these things. You had to know from using numbers. So if you want to check later, I put the solutions up, and you can check them. There's 5/17, 1/13, and down here is 23 over 99. It's Michael Jordan as a repeating decimal. I just thought it'd be cool. 2, 3, 2, 3, 2, 3. There he is. So math teachers want you to have a number sense, and the reason we want you to have a number sense is because then you can spot things that you might not be able to see otherwise. Here's what he was able to spot. How did Euler get trig from this problem? He created an integral, and then using some tricks, solved the integral. At least approximated it. He showed it was really close to 1.644924. And then he said, hey, that looks like something else. If you were to do it by hand right now with this computation of the sums of the reciprocals of the squares, you need 30,000 terms to get out to what he did. 30,000 terms. I did not actually go to 30,000 terms. Remember, you don't get a calculator. I noticed none of you were even trying it with the calculator. You wouldn't want to. Where does the trig come from? The kid could calculate, and he recognized something about this number right here. He recognized that this number is related to pi. Do you? Does it look like pi? What's pi? 3.14-ish? But it's certainly not pi over 2. Pi over 2 is 1.57, so it's not that. But that's what I'm saying. This guy spent his time doing math. And because of it, he got really good. He was able to spot something. He spotted it, and what he did is he saw, hey, that looks really close to what I think of as a number. I wonder if I could make a solution that would fit. Have you ever flipped to the back of a math book, seen the answer that's in the book, and then tried to go back and figure out how to make your work match that? That's what Euler did. I'm not going to tell you what it is, but I'll tell you what he did. He took sine and wrote it out, and then he looked at it and he said, that's cool, but that's not the one I want. I'm going to divide both sides by x. So now I have sine of x over x, and of course that reduces the power of x over here by 1. Okay. Some of you are still looking at that going, what? At this point he said, okay, I'm going to hit pause on that. Just leave it where it is. Because I got to do something different now. Pause. Those of you who are in intermediate algebra, you might remember a function that has roots of 2 and 5. Because I put it up there on the board earlier. And if it has 2 and 5 as roots, you can write it in factored form. X minus 2, x minus 5. If you had a function with roots of plus or minus 2 and plus or minus 5, you could write it out with the 4 roots, right here. And Euler was like, hey, I like that idea. Let's try it. The sine function has roots. It has roots of 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and also negatives. So he just wrote them all out. He wrote sine as a factored group of roots. Didn't seem like much at the time. And notice it has an x in front, so he divided by x to make it look like what he had before. And he looked at all of that and he said, you know what I'm going to do? I'm going to multiply all of those out. Wait, that's what he did. He actually did this. And so what he did is he multiplied them all out, but he only cared about the x squared term. So that's the only one we're going to look at. The way you get x squared is multiply this by the first, this by the first, this by the first, and if you take a look, it's here. And you notice anything common to all of those?
Pi squared.
Pi squared to every single one of them. He saw that too. So what he did is he factored out the pi squared. And take a look at what remained. That's the thing we were hoping for. The 1 plus 1 over 2. Hey, it's right there. This is where he said, like we do in math sometimes, we work one side, he had the other side, and then he put them together. So this negative 1 over pi squared times that stuff is actually the same as the x squared coefficient here, which is just negative 1/6. So he was able to set these equal to each other and solve, and he showed that the sum of the reciprocals of the squares is pi squared over 6. I checked our Larson book. This is one of the homework problems now. That's right, something that it took the greatest minds in existence more than 100 years to solve is now, anybody can do it. So easy. So easy. So here's what it means. If you know the sum of those reciprocals is pi squared over 6, then your probability is 1 over that. Your probability turns out to be 6 over pi squared, which is about 60% of the time. If you put all of those numbers into the hat, from 1 to infinity, what are your chances of picking two numbers that are relatively prime? A little bit better than 60%. Again, Euler had some good things going. So here's my wrap up. This is pretty interesting. You might have thought that the final solution involved this. Pi. Haha. Did it? Yeah, it kind of did. Well, you've heard people say pi r round and there's a math joke. Wrong. Pi r squared. Have you ever heard that one? Yeah, pi r squared. Because the area of the circle pi r squared. Okay, that worked out really good. Thanks. Thanks, way to leave me hanging on that one. It actually turned out it's not pi r squared, it's pi squared. Squared pi.
Who's laughing now?
So this is a picture I found online of someone who made a pie in a cake pan. It's squared pi. But our solution just has to be one of those pieces. This piece right up here is squared pi over 6. And that's what Euler came up with in his solution. So anyway, I hope you had a chance to see some pretty interesting probability, as well as some math and how it kind of came together. In the future, I've got some other things that we could put on if you're interested, but I'll stick around if you have other questions, we can talk. So that's it.